So in this video, we're going to take a look at our project, and our next project step is for you to determine from experimental values of hysteresis loops for a 1070 steel the K prime and the N prime, the parameters for the Ramberg-Osgood cyclic stress strain curve. Now we've kind of talked about the idealized situation in the previous lecture. And when we look at the real data, there are a few things that come up that we have to account for and understand what's going on. So let's look, if I can find our project description here, exactly what we're going to do. It says, determine the cyclic properties K prime and N prime for 1070 steel from the data set supplied. You're going to plot the hysteresis loops, compare your calculated constants and the monotonic Ramberg-Osgood curve equation using the cyclic properties. And then you're going to use Massing's hypothesis, or the hysteresis branch equation, to see how well your constants do with modeling the branches of the hysteresis loop. Now the next couple bullets here are for, we'll make a separate video for MS6000 sheet steel. Alright, so let me find our data that we're going to look at. It's in our project materials folder, and there's a 1070 steel, and this is an Excel file that I just created. But what you'll see are these different text files in this README file. It's worth taking a look at the README file very quickly. It explains what's going on in here. It's 1070 steel. Stress values are in megapascals, and there are actually three columns. One is stress, then there's strain in the axial direction, and then there's diametral strain. We're not going to have need for the diametral strain in this case, so we're going to ignore that particular column of data. But since this is a steel, we're going to take E as 210 gigapascals. And I have a note here that the tests were conducted on one specimen, and that Yanyao Zhang, who was a fellow graduate student with me at the University of Illinois, created this data in 1992. He did these test measurements. It's been a little while. I've been using this for several years in the fatigue analysis class. Alright, so the first thing that we're going to do is I'm going to have you load in the hysteresis loops into Excel. Now, there's some low strain, and that's basically a very small, thin hysteresis loop. And then there are two sets of hysteresis loops for several of the other strain levels. And one of the things you'll notice right away is they don't exactly fall on top of each other. They're pretty close, but not exactly the same. And I think the biggest one, there's only one set of data. So these were ramped up and then ramped back down, and we talked about how to do that in class. Alright, so ideally everything would be on top of each other, and ideally everything would be nice and perfect. And ideally what you would do then is you would find the modulus of elasticity, and you would look at the tips of these loops. You would make a plot of the log of the stress amplitude. Let's call it delta A over 2. Delta sigma over 2. And the log of the plastic strain based on the hysteresis loops. And ideally they'd all be on a straight line. The slope of that line would be related to the N prime. And then the intersection point, if this was extrapolated out to a strain of 1, a plastic strain of 1, would come over here and intercept at K prime. So you would have like this largest hysteresis loop. You would calculate the plastic strain associated with that would be the total strain minus the elastic strain, which would be the stress amplitude divided by the modulus of elasticity. So these would all be amplitudes. And you would plot that and get all this out. Okay, there's going to be some things that show up with this data that make this maybe a little bit more difficult than what it seems based on this perfect best case scenario. The other thing that I want you to do then is once you find your K prime and N prime, I want you to plot your stress strain curve versus the data. Now if it looks really good, then all those tips will have the lines that go through it. It can be very sensitive to what you call K prime and N prime, and so these, it may not be as perfectly going through these tips as what you might think. You may have to do some post-fit adjustments to the data. Okay, so this will be an important thing to do. Don't just trust the K prime and N prime that comes out of the plot that you make in the regression analysis, but actually go through and see if it does a good job in fitting the actual test data. The next thing I want you to do then after that is to see how well the Mastings hypothesis performs. Now remember, the Masting hypothesis is the branch equation. So you're going to start at the tip of one of these hysteresis loops, and you're going to decrease the stress, and you're going to use your K prime and your N prime, and you're going to see if it follows the branch or if it doesn't follow the branch very well. And then you may need to adjust your K prime and N prime again. All right, so what I'm going to do in the next step here is I'm going to bring all the data into Excel, and we're going to take a look at it, and we're going to make a plot, and we're going to take a look at the raw data. We're going to adjust the raw data so that the hysteresis loops are centered. Let me make another slide for that. Now, as a consequence of the way this test data was collected, and as a consequence of just doing testing, not everything is going to be perfect. I'm going to exaggerate a picture here so that we can see what's going on. So there is the origin of our stress and strain system, and our hysteresis loops aren't going to be perfectly centered. Now, I'm really going to exaggerate this just to make a point here that this may be the actual center of the hysteresis loop, and what we want to do is we want to move all of this data to the origin of the coordinate system that we're using. Okay, so how do we do that? Well, if we look at the strain values, maybe this is epsilon maximum, and this is epsilon minimum. Assuming that the hysteresis loop is pretty well symmetric, and I think you'll see that it is. Assuming that the hysteresis loop is pretty well symmetric in shape, if we take the average of those two values, that'll give us to the kind of geometric center of this loop. And likewise, if we look at the maximum stress and the minimum stress, If we take the average of those two values, then that'll give us the up and down value. It'll give us the location of the y coordinate of that particular point. Okay, so now that we have the center and we have our actual data, what we're going to do is we're going to take all of this data, the red hysteresis loop, and every single point we're going to subtract off those two values, and that will bring us to the center of our stress strain coordinate system. So now this hysteresis loop should be centered. Let's see if I can draw that. Oops. Now you might say, well, the real test data is off-center. Why don't we just use the real test data? Well, we're trying to look at the idealization. Okay, so there's lots of things that can happen with transient material behavior and so forth. But our model for our cyclic stress strain curve and our hysteresis branch is going to assume that we have something that starts off very nicely centered at the origin of our stress and strain plot. And so in order to come up with those constants, we want to kind of get everything to fit that idealization. So that's why we're doing that. Alright, so I'm going to pause the video, I'm going to load in all the test data, and then we'll see what we can do next. Okay, so here's all my data in Excel, and here are the different files: A2, A4, 6, 8, 10, and then B8, 6, 4, 2, coming up and then coming back down. And in here I have the axial stress, the axial strain, and then there's also the dimetral strain, which again we're not going to use. But let's just plot this raw data and see what it looks like. So I'm just going to get in here and I'm going to insert a plot of some sort. Let's see. Oh, it's in compatibility mode. That's fine. So we'll do a scatter with a connect the lines plot. I'll tell you what, let's just do a line without the data points. So let's see what that looks like. Alright, so I'm going to right click, I'm going to select the data, I'm going to add a data set. I don't really need a series name. My X values are going to be the strain. Now hit the end and the down arrow to get that. And my Y values going to be the stress. And let's see what that plot looks like for that data set. Alright, so here's kind of a thin hysteresis loop. It looks like we have a little bit of plasticity. If we had no plasticity, this would just be a straight line with a slope corresponding to the modulus of elasticity E. Okay, now what I'm going to do then is I'm going to pause the video and make the rest of this data show up on this plot. Okay, so I'm about halfway done. I've got all the A loops plotted, and I have the 10 loop plotted, the 1%. One thing I want to point out about the data is there's a little bit of gap in here. You can kind of reasonably kind of think what it might look like to connect those points, but it was data acquisition issue that we had during this time, and we didn't get all that data from this point. So there's only so large of a buffer and so forth. But that really won't affect our analysis. But I did want to point that out, that some of the data just didn't get collected. Alright, so what I'm going to do is I'm going to continue doing this and plot the other loops, and I might make some adjustments to the color. We'll see. But I'll just make a few more additions to this chart. Okay, and so there's all the raw data plotted together. We can make it look a little more squished in if we want. Okay, so those are some nice hysteresis loops, but I do want to point out that if we look at some of this, there are some differences between the two, the hysteresis loops on the upside and hysteresis loops on the downside of how this data was constructed. So they're generally pretty close, but there are some slight differences. Actually look like they match up pretty well on the compression side, but there's a little difference on the tensile side. All right, so what we're going to do then is we're going to work with this data a little bit, and we're going to center the loops as we talked about. We're going to find the coordinates of the tip after we center it, and then we'll do some regression analysis on that. All right, so what I've done is I've copied my spreadsheet, and I've made a new plot using the centered stress strain data. So remember, we talked about how to center the data. So here's my axial strain and axial stress. I went ahead and put it in this fashion instead of stress and then strain to make it easier to plot. The x values are the axial strain and the y values are the stress. I found the max and min of that data, and I took the average of it, and then this centered strain is the uncentered strain minus this value, and likewise for the stress. Based on that, then I calculated a plastic strain based on the total strain minus sigma over E using the centered data. And from that, I was able to search through the data and identify the tips of each hysteresis loop. Okay, so this is the strain, and then the plastic strain and the stress. And as we talked about in the lecture portion, we can make a plot of the tips of the loops, the stress amplitude, and the plastic strain amplitude, and fit that to a power law. Okay, so this is log scales, log scales, and here's all the hysteresis loop tips that I have. And you can see that with this coefficient, here's the K and this is the N, 1092, 1093, and 0.1203. That's the K prime and the N prime fit. However, those hysteresis loops in the beginning, they didn't quite fit very well. Okay, so we're probably maybe better off ignoring those first two ranges and looking at the rest of the data. And that's what this plot is, by throwing out a couple of data points and fitting more in this range over here. Okay, we get 1683.2 and we get 0.1969. Let me write those numbers down. And I want to write those numbers down because I want to check and see if the data looks good using those values. I'm not sure which one is the best one to use. And this is what I want you to do. I want you to come up with your best looking set of parameters. I'm expecting most people will have different values for these things. It'd be unusual for two people to have the exact same values. Depending on how you do this, let's see what these extremes give. Okay, so I'm going to have another plot where I put in the cyclic stress strain curve and I plot that against all this data. Alright, so we see a couple things in this plot. Now, for right now, I want you to ignore the dark red lines. We'll talk about that in a minute. But focus on the tips of the hysteresis loops and this kind of greenish line that comes out of it. So this was my first fit that I tried, the 1093 and the .120, where we included those two hysteresis loop tips. I don't know, it sure it fits kind of this beginning part okay, but it doesn't do a very good job out here. If we have a significant amount of plasticity, we might want to be able to fit this higher plasticity range a little bit better. So let's try the other set of numbers I got, the 1683 and the .197. Okay. So that in fact does seem to do a little bit better job of fitting the data out on these hysteresis loops over here. Alright, so I want you to see how good of a fit you can get, and in fact I'm going to use this spreadsheet to check your work. If you come up with some crazy numbers, I'll be able to look at my plot and say, hey, this doesn't look anything like it's going through these tips, or I can say it looks pretty good. But the other thing I want you to test out is how well your fit does in modeling the massing hypothesis, the hysteresis branch equation. And remember that delta epsilon over 2 is equal to delta sigma over 2 divided by E plus quantity delta sigma over 2 divided by K prime to the 1 over N prime power. And that's what these equations show here. Now, they're not going to be perfect, and this may not even be as good a fit as what we can do if we tweak these numbers just a little bit. So ideally, this branch would go and follow this curve right here and end right about at this point. Likewise for these other hysteresis loop branches. And then it would pick up from here, and we could model the other half of that this way as well. So I'm not going to play around with this anymore, but I think you have the idea that I want you to see how well you can adjust these parameters to fit our actual test data. Don't rely solely on these log-log plots. Really what we're trying to do is model both the elastic and plastic response of the material. So you might even want to just plot the plastic strain calculations and not the total strain, but in the end we want to make sure that the total strain plot does look good. So with this kind of spreadsheet, I found that I can kind of tweak these values and kind of see, so this one kind of is a little too stiff and it doesn't have enough response. So you can probably narrow it down and get a nice looking model for K prime and N prime based on this 1070 steel data. Okay, so as part of your writing assignment for your for the final project, go ahead and write up what you did, how you did it, and what your values of K prime and N prime are.